I, um, is my voice audible? Could you anyone confirm if my voice is audible? We'll start in a few more minutes until more people join. Um, Please let me know if my voice is audible. If someone is not able to hear, can you let me know in chat? So we'll start in few more minutes. We're still waiting for more people to join. So today is the last lecture class for this course. So we will be just covering the last topic and also summarizing all the topics that we have done till now. So, okay, so I'm sharing my screen. So please let me know if you're able to see my screen. Okay, I think we have a fair number of people, so I think we should start now. Um, I I hope my voice is audible and you are able to hear me, and you are also able to see my screen that I'm sharing. So we are at the end of the last class, which is lecture week 8 or the last lecture for this course. So I hope you uh, for this last lecture series we'll be covering the week 8 topics as well as if we get time we also just do a quick recap of all the topics that we have done till now. Any questions or anything meantime we can cover. And yeah, so this would be the last lecture series, and then I think we would have your exams on uh, soon. And so let's start it with few, 2 3 minutes once more to do that, so that okay. We'll cover the topic on dynamic programming first today. Then on some of the applications like longest common subsequence, matrix multiplication, and lastly, like we do a quick wrap up, sort of in terms of like all the topics, almost like a summary of all the topics that we have done till now, and then we'll do some of the languages, common languages, difference with that, and so on. So that's the goal for today. So we'll just quickly go through dynamic programming basics first, so that I guess you already know this, but for people who are not familiar with that, so probably just a quick sort of like, uh, uh, quick sort of like recap sort of what dynamic programming is and what it means. So yeah, so let me know if you're able to see this tab now. So we'll just quickly go over through the aspects of dynamic programming so that everyone is acquainted with the topics and the overall theme of dynamic programming. So dynamic programming is basically like an algorithm design technique, and it's a technique for solving problems that have some kind of optimal substructure property. That means that you can do some sort of recursion in the thing, and it also has something called this concept of overlapping subproblems. So that means the problems that you're subproblems, the problem that you're dividing into subproblems, you have overlapping structures that you can see. So we'll look at some examples. I think that should give you some fair understanding. So if you're not able to hear me clearly, please let me know in the chat if there is any issues with my audio or something. So we'll keep today's session short, I think, because it's the last lecture series anyway. So we won't be taking up like we won't need the entire time slot since it's only a few topics for today. And we'll just go through it once uh, the entire things are done. Okay, so I think we have a fair number of people, so I think we can start now. So again, we were discussing about the concept of dynamic programming. So basically, it indicates having an optimal substructure property where you can apply recursion as well as we have some property called overlapping subproblems. So overlapping subproblems, as I mentioned, is that you divide a problem into different subproblems, and you would see like they have some kind of overlapping structure. So the idea is that do not repeatedly solve the same subproblem, but solve them only once, and we store it in some tabular format, uh, which is called like a dynamic programming tool. So because the thing is that if you because many of the subproblems we see they would get repeated over time, and if you solve each subproblem again once more the same subproblem, the running time would actually sometimes in many cases it will be exponential time. So to limit that, usually what people do is like they solve one of the single subproblem, and when they find the same subproblem in the same thing, they instead of solving it from scratch again, they just query the subproblem solution from a table itself. We'll look at some of the examples what it means. So one popular example of this is the Fibonacci numbers. I think we actually covered the Fibonacci programming sort of in the initial one or lecture two, where we were discussing about how to code a Fibonacci series using recursion. So now we'll look at some aspects of how to solve this Fibonacci thing using dynamic programming. So just to give you a recap of what Fibonacci is. So Fibonacci is like a series. So where the number at the um, nth position is actually equal to the number is actually equal to the sum of the previous two consecutive numbers. So basically that means is that I start with 0 and f1 I start with 1, and f of n is equal to, I define it as f of n minus 1 plus f of n minus 2. So that means the previous two consecutive numbers, I'm summing it up and I'm getting the current f. So 0, 1 I started with 0, 1, and then for the third position I just do 1 plus 0, which I get 1. For the fourth position I do 1 plus 1, I get 2, and so on. So there is this thing called the hallmark of dynamic programming is that you have something called optimal substructure. So that means an optimal solution to a problem or an instance um, also contains optimal solutions to its corresponding subproblems. And so when I say the word subproblem, basically it means that I'm invoking something called recursion, because recursion basically means that you are invoking the same function on a smaller parameter on a smaller data, let's say. So, for example, fn, when I define the function Python function fn, I what I do is like I do a recursive call to fn f of n minus 1 plus f of n minus 2, and so on. So now, if you check this recursion tree, so this is like a recursion tree which we have created. This one, yeah, do the video was in that. Okay, so if you see the recursion tree here, so f of n is basically f of n minus 1 plus f of n minus 2, and f of n minus 1 I can again divide it into f of n minus 2 and f of n minus 3. And f of n minus 2 I can again divide into f of n minus 3, f of n minus 4, and so on. So as you can see, like I'm breaking down the problem into different subproblems. So f of n I'm breaking it down to the problem f of n minus 1 and f of n minus 2. Similarly, f of n minus 1 I'm breaking down into f of n minus 2 and f of n minus 3, and so on. So that's like something like what we call as breaking our problem down into different subproblems. So now this is like the thing, like this is one of the hallmark of the dynamic programming is that we solve for the subproblems first. That means f of n minus 3, f of n minus 4. And once you do this subproblem solving, you then transfer it to the parent problem, that is f of n minus 2. And it goes back until it reaches the root of the tree. So now we also discuss something called overlapping subproblem structure. So that is one of the second feature of dynamic programming, which is this thing called uh, overlapping subproblem structure. So if you see here, f of n minus 1 actually makes a call to f of n minus 2 plus f of n minus 3, and f of n minus 2 also makes a call to f of n minus 3 and f of n minus 4. So basically that means f of n minus 3 is getting repeated twice here. So f of n minus 3, if I break it down again into its corresponding subproblems, it would be f of n minus 4 and f of n minus 5. Similarly for here also it would be the same thing. But so the thing is that I am getting the same subproblem on both the two sides for solving one for f of n minus 1 and for solving f of n minus 2. So what if I do something like this? So basically, if I consider the runtime is exponential because the Tn, let's say Tn is the runtime, and the upper bound is 2 to the power n. Because why is 2 to the power n? Because I would have at max. So at the first problem, I have something like one problem. Let's say I am dividing into two problems. Then I'm dividing into four problems, and then I'm dividing into eight problems. So you see it's kind of getting squared, the number of subproblems. So first one, then two, then four, then eight, then 16, 32, and so on. So it goes in powers of two. So that's why my upper bound is always equal to 2 to the power n, and my lower bound is something called 2 to the power n by 2. And I'm not going to the deep analysis of this. You can see easily it's provable why it's the lower bound is 2 to the power n by 2. But I'm just saying the upper bound is the worst case scenario is 2 to the power n. Worst case basically means that you have to solve all the subproblems. So runtime is exponential, but we see that we are repeatedly solving the same subproblems. So that means if we solve f of n minus 3 and then again we solve f of n minus 3, so we are doing some kind of repetition. So what if we store the solutions in some kind of table so that when we encounter the same subproblem after some time, we don't have to repeat the same solving of the solution subproblem. So you can simply do query to the table where you sort of recorded the solution, and then we can just use it. So then my runtime becomes very less than exponential. So overlapping subproblems basically means that a recursive solution that contains a small number of distinct subproblems that are repeated many times. So there are two variants of dynamic programming, something called as bottom-up dynamic programming, often referred to as this vanilla dynamic programming itself, the bottom-up, and the other is something called memorization. So memorization is something which is a part of this week's lecture. So we'll cover that shortly. So first we discuss about bottom-up dynamic programming algorithm. So what you do is like you store a one-dimensional dynamic programming table for the Fibonacci problem, and you fill in a bottom-up fashion. So for example, if you have a table like this, for the first ID you stored at, let's say, 0, and because f0 equal to 0 for the second item in the element is stored as 1, because f1 equal to 1 and so on. And so what you do is like you define this thing. So uh, this is uh, this is written in pseudocode, but since we are working with Python, I think it's very easy to also see how you can just convert this pseudocode to Python also. So basically, you have Fibonacci bottom up DP is a function. You do def of Fibonacci bottom up DP. N is your parameter. Initialize this table. So F is like an array in your Python. So it's a 1D array in your Python, or you can think of it as a list of list actually. So f of 0 initialized to 0, f of 3 initialized to 1, and what you do is like for I equal to 2 to n. So in Python you can just simply do for I equal to for I in range 2 comma n plus 1, because I am having an equal to sign to n, so that's why my range has n plus 1 at the end. I simply do f of I equal to f of I minus 1 plus f of I minus 2. Basically, what I'm doing is that the list element at I minus 1 plus the list element at I minus 2, I'm just adding them, and I'm getting list of the element at position I. And finally, the final solution will be stored at the end of the list, which is f of n. So I can initialize a list of numbers uh, of size n, and then I do this operation. There is only one for loop. I only need order of n time, because I'm only running the loop one time through all n, so it's order of n. And space is also n, because I'm considering a list of size n. So that's why time space both is n. So you can see like it's reducing from exponential to just a linear time space algorithm now. So this is the essence of dynamic programming, and this is something which we call as memorization also, because what we are doing is like we are actually storing the numbers fi, the solutions into the list itself. So whenever I need to get a solution, I can just query it by the corresponding index value. So memorization basically is like it uses a recursive algorithm. So after computing a solution to a subproblem, you store it in a table, and subsequent calls checks the table to avoid redoing the work. So in case of memorization, what you can do is something like this only. Um, so one was the previous style of writing. Now it's like something like Fibonacci memorization as a function n, where if I for all I am initializing it to null value. You can think of 0 also, and then I'm again calling a different function, Fibonacci memorization REC, which is basically short form for recursion, n comma f, and I just return f of n, which is the final solution. So if I go inside the function fib memorization rec, I would see that if f of n is equal to null, that means it's my initial state now, and if n is equal to 0, I just initialize to 0. If n equal to 1, I initialize to 1, or else what I do is like I recursively call the same function for n minus 1 and for n minus 2. And same thing you would see like you get the same order of n and space of on itself, because because we are doing memorization, so that's why we are not solving the same problem multiple times, so you would get order of n and space on. So okay, so any questions up till now in this point? So we have already covered, I think, memorization is this part of today's lecture series. Any questions in this part today? Okay, I think we can go ahead. So we'll look at some another new problem, which is called longest common subsequence, which is also part of today's lecture. I mean the topic for week 8 also. So we'll look at longest common subsequence. Um, so the basic idea here is that you are given two sequences. You can think of in this sense as a Python list actually. Two Python lists you are given, x of 1 to m and y of 1 to m, and you want to find out the longest subsequence common to both of them. For example, and so basically an important point to check here is basically I'm saying a longest subsequence, not the longest subsequence, because there might be different subsequence of having the same length. So I'm just saying here to print only one particular subsequence, which is the longest. So there might be multiple subsequences which is a similar length, and it's also the maximum subsequence. And this the problem is basically asking you to just print only one particular subsequence, any one of the particular subsequence. So here is an example: x of a, b, c, d, and so on, and y is so on. So you want to print the longest subsequent common subsequence. So I see B and B are common, C and C are common, B and B are common, and are common. So BCBA is like the longest common subsequence here. So LCS x comma y is like a functional notation that we are using. It's something which is the longest common subsequence function. So what is the brute force algorithm that we can use? So one of the brute force algorithm is that what you can do is like you check for every subsequence of elements that you see here, and for every pairwise subsequence, you see whether or not I'm getting a subsequence. So there would be 2 to the power m subsequence of x because each bit vector of length m determines a distinct subsequence of x, and hence the runtime in this case would also be exponential because it's the order of 2 to the power n or 2 to the power n, whichever is larger. So the runtime would be exponential. So we construct a dynamic programming algorithm. What we do is as follows: we look at the length of the longest common subsequence, and we then extend the algorithm to find the LCS itself. So we denote the length of a sequence as s by mod of s, and we consider the following: we consider the prefixes of x and y as follows. So we define c of I comma j as the length of LCS of x of 1 to I and y for from 1 to j. So basically, the sequence x and chunking the sequence x from 1 to I and the sequence y and chunking from 1 to j, and then finding the LCS of them and then calculating the size of them. So my C of m comma n is basically the final result that I want, which is LCS of x comma y, the length of it. So basically, what I can say is that C of I comma j is C of I minus 1 comma j minus 1 plus 1 if x of y is equal to y comma of y j. So that means that the ith position x position the element at position I of x and the element at position j of y, if both of them are the same, then I simply decrement the pointers to the previous I minus 1 and j minus 1 and repeat the process. Else, what I can do is like I take the maximum of c of I minus 1 comma j or c of I comma j minus 1. That means I can decrement for y and check the sequence between x and y then, or I can decrement x and check the sequence between x comma y. So either one of them, which is maximum, it gives me the thing. So this is my recursion problem. So any questions here, because this is something might be a bit tough to understand initially. Any questions in this point? Okay. Uh, so then I think it's fairly straightforward now. So I just have to repeat this process, and I can simply similarly do memorization concepts apply here also, and then I can just solve it. So I'm not going to the proofs here this because it's out of sort of thing here. So as I mentioned, so to compute the LCS, any prefix of z is an LCS of prefix of x and a prefix of y. So basically, this is the main particular intuition that we are using here, which is basically a part of the optimal substructure that we are utilizing in the longest common subsequence problem. Okay. So if I just show you a recursion tree of this thing. So LCS of 3 comma 4 is basically, I can do, I can decrement for, let's say, uh, for the x value, so I get 2 comma 4, or I can decrement for the y value, which is 3 comma 3. Here what I do is like 2 comma 4 I am decrementing for either for x or decrementing for y. So 2 comma 4 I can do go to 1 comma 4, or I can go to 2 comma 3, because I'm decrementing from 4 to 3. And if you see here also 3 comma 3 I can decrement go to 2 comma 3, where I'm decrementing x. So as you can see here, there is again a case of same subproblem that we are seeing here. So the total height is of the tree is n plus n. M is the size of the list x and n is the size of the list y. And so, and the entire thing is potentially exponential, because again we are having multiple leaves of the tree, multiple children of the tree. So it's like exponential. So we can resolve this by solving the subproblems only once. So repeating subproblems we can just solve once and then store it somewhere and then we can use. So that's the same concept that we use for the Fibonacci thing itself. So so the distinct LCS subproblems are all the pairs I comma j. The number of such pairs for two strings of length m and n is only m into n, because I only need pairs. Total number of such pairs would be only m into n. But as I see, I'm actually getting more subproblems. But the distinct subproblems are actually m into n only, because that's the total number of subproblems pairwise I can clear. But it becomes exponential because there is a lot of repetition in the same subproblem. So I can simply do memorization, as you can see here. So after completing a solution to a subproblem, we stored it in a table, and subsequent calls to check the table to avoid redoing the work. So you initialize Cij equal to null, and if I equal to 0 or j equal to 0, either of them you initialize to 0. Else you take the condition, first condition in the recursion equation that we showed, x of I equal to y equal to j. If that is the case, then you simply do Cij equal to LCS of x comma y, I minus 1 and j minus 1 plus 1. Else you take the maximum of either of the two, where you decrement either I minus 1 or you decrement j minus 1. So here you decrement x and here you decrement y, and that's your the final answer is actually stored in the C of I comma j. And so the total time taken would be order of m comma n, because you're running a loop kind of over the entire list of x, and again running a loop over the entire x of y, entire length of y. So m into n, but you only require constant work order of 1 per table entry. So you're basically storing in a 2D table sort of 2D array or 2D list, and that's why it's order of 1 or constant per table entry. So that's my recursive formulation setup. This is my recursion equation, and this is my sort of so from C of I comma j, I can either go to C of I minus 1 and j minus 1, or I can go to C of I minus 1 comma j, or I can go to C of I comma j minus 1. So I have three sort of possible directions I can go, and either of this direction, or either the left or the right, or either the left or the top, I take the maximum of them. So C of I minus 1 comma j and C of I comma j minus 1, I take the maximum of either of the two, or I go to the diagonal one, which is at the top diagonal. So um, this is basically a dynamic programming, the table actually, where we are storing all the sort of values. So I would suggest you to just go through the table here once. Maybe you could pause here for a few minutes so that you understand how we are computing. So we are starting from here, 4 comma 4, and you see like how you are computing the table sort of. So you have your sequence A B C D A B D A, and you have your sequence here as for Y, and just see follow the equation of the arrow, the arrow direction, and see like if you are able to, if you are clear about the concept. Okay, I think I hope you are able to understand through this. So any questions till now? We will probably go to the next topic of matrix multiplication problem. Um, all right. Yeah, I think the last topic for today would be on matrix multiplication because that's the beginning topic on dynamic programming. So again, so it's very similar to longest common sequence subsequence problem itself. Um, okay, so there is a question in the chat. So if you could explain the table. Yeah, let me explain the table what it is meaning. So so the table actually is storing, as I mentioned, the cost, the Cij, the cost that I'm storing. So basically, I have the cost Cij is equal to. So I'm initializing it as 0 comma 0. If you see the equation here, so Cij equal to 0 if either of I equal to 0 or j equal to 0. So at this point I is equal to 0, j equal to 0. So all the columns here is initialized to 0 and all the rows here are initialized to 0. Now what I'm doing here is as follows. I even go back here. I see like if x of I is equal to y of j, then I simply do I minus 1 j minus 1 plus 1, or I do maximum of either of the two. So from here you had 0. So now I'm comparing this a and b. So a and b, x of I is not equal to y of j. So that's why I'm taking I'm decrementing either j minus 1 or I'm decrementing I minus 1. That is, I'm decrementing from y or I'm decrementing from x. And accordingly, I'm computing the next value here and so on. So if you see here, 0, comma 1, I see I add the extra additional cost, and so this cost gets added up over time, and at the end you get the final solution, which is stored as the longest common subsequence, the length of it, which is equal to 4. So the 4 is the correct answer here, which is DCBA is the longest common subsequence, and the length we want to find the length. So my correct answer would be lying at the bottom right corner, which is C of n comma n, which is the this thing. So that's the how you interpret the table. So this is your like memorization table. So you can just simply query from the table C of I comma j, any of the tables, and so you can retrieve it and you can solve it recursively. So that's the main idea. Okay. So so I think only the last thing remaining is the matrix multiplication case of dynamic programming. So we'll just go through that also, and we'll just discuss briefly what is the problem statement there. If anyone is not, kindly unmute yourself. Um, okay. We'll look at dynamic programming for matrix chain algorithm. So this is based upon some lecture notes from another like lecture notes from another course actually, just to sort of give you a broad insight of the understanding of the whole. Yeah, so we'll look at this concept of something called matrix chain multiplication. So suppose that we want to multiply a sequence of rectangular matrices, in which order we should multiply. So let's say I have A, B, C as three matrices, and we want to figure out in which order we should multiply so that the cost of multiplication is very less. So I can do either A first, I can do B and C, and then multiply with A, or I can do A and B first and then multiply with C. So either of these two is the options. So basically, I mean, like everyone knows what is a matrix is, so I'm not going into the details here. So, so in matrix multiplication, let's say A is a n cross n matrix and B is a n cross p matrix. So the product of A and B is basically a n cross p matrix AB, whose ijth entry is defined as the summation of aik and bkj. Basically, if you see the previous solution, basically you are uh, if I have another matrix on the right hand side of A, you just do row and column wise, you just do multiplication, right? So that's why you have a summation sign and you just do AIK DKJ. So basically, AIK basically means the element of the matrix A at position at row I and column K, and similarly, this is it. So in other words, we multiply the entries of the ith row of A with the entries of the jth column of B, and we then simply add up. So I hope this portion is clear. So I'm giving you this sort of problem here just to verify if everyone is on the same page. So just understand how we are computing the matrix here. Yeah. So if you have any questions here, because this is like a basic thing. So if you have any questions here, feel free to ask in the chat. So maybe like 1 minute we can just 1 or 2 minutes we can just look at this if you are understanding the operation correctly or not. So yeah. Okay, I think you probably have like got a understanding of what it means here. So basically we are doing column wise and row wise matrix multiplication of two matrices A and B, and so we have A11 A12 into B12 of B22 and so on. So I guess like this is just a notation wise thing. So I guess that's clear. So we first calculate the complexity of matrix multiplication. So let's say A is an n cross p matrix and B is an n cross p matrix. Thus, AB is like a n cross p matrix because it's obvious. N cross m into n cross p, we get n cross p as the matrix. And computing the product AB takes total n into m into p scalar multiplications, and it takes n into m minus 1 into p scalar additions. So whatever additions you are doing in terms of summation of AI, AKJ, BKJ, those things are your falls under additions. So that's the idea that we have. Um, so this is like a standard matrix configuration algorithm. So the chain order problem now is the main problem in the dynamic programming setting that we want to discuss. So we know matrix configuration is associative, meaning that ABC is basically into BC first and then A. Therefore, if we have a choice of forming the product of several matrices, what is the least expensive way to form a product of several matrices is the naive matrix multiplication algorithm is used. So we use the number of scalar multiplication as the defining factor for cost. So basically, we want to find out in what order we should have this matrix multiplication done so that we have the minimum number of scalar multiplications. So suppose we have four matrices now. Let's say 30 plus 1, B is 1 cross 40, C is 40 plus 10, 10 is 10 cross 25. So now the thing is that let's say I just want you to verify this thing. So let's say AB and then CD. AB and CD, like how many scalar multiplications do you need? So it comes out to be 41200. Why is the case? Can anyone confirm in the chat? Yeah, so there is a question in the chat if the Python program exam is MCQ. Yeah, it would be a combination of MCQ and some numerical kind of problems also, not multiple choice all the time. So, okay. So so basically now we have four matrices here as we were saying. So completing A into B would take me around 30 into 40, 30 into 1 into 40, which is 1200. Is my final cost for that. So I get a 30 cross 40 as my matrix now, dimension for AB. For CD, I need 40 into 10 into 25 as my final scalar multiplication. So if you add 1200 plus 40, 400 into 25, something like that. Plus we also have 30 cross 40 now into 40 cross 25. That means 30 into 40 into 25 as the final matrix value. So what else if you do the entire calculation, it turn out to be so much 41,200 scalar multiplications. But if you do this now, let's say you first do with BC and then with BC, then do with D, and then we do with A. So it requires you further less calculations in that sense. So that's the kind of thing. If you see the ordering now, it only takes around 1400 scalar multiplications. So the matrix chain order problem is basically such that you have a matrix A1, A2 up till AN, where AI is a DI minus 1 plus DI matrix. What is the minimum number of scalar multiplications you need to do? And in which order do you want to do? So you focus on question one only. So possible solution is that you try all possibilities and choose the best one. So basically this is a brute force condition. So there are too many of them, exponential in the number of matrices to be multiplied. So you need to be smarter and you should try something called dynamic programming as we are discussing. So that's the kind of update here. So yeah, I will just come to the chat questions once the this portion is done. I think after that, I think we will just do a quick recap of all the topics and also come to the queries. So we define Mij to be the minimum number of multiplications we need to compute AI plus 1 up to aj, and the goal is to find m of 1 comma n. 1 basically means that I'm starting from a1 to an. So I define m of I comma I equal to 0, and I do apply recursion here. So how I define Mij recursive. So one way is to do this. So I can do consider all possible ways to split AI through AJ into two pieces. Compare the cost of all the splits, the best case cost for computing the product of two pieces plus the cost of multiplying the two products. So basically, this is the equation that I need. So I take a partition sort of at k from A1 to AJ. So I do m of I comma k plus m of k plus 1 comma j, the minimum of this thing plus bi minus 1 dk dj. So this is my matrix cost for multiplication of ai, ak, and aj in order, and I find the minimum k for which this thing is happening, and I do this recursively. So minimum cost to compute m of I comma k basically means that a1 up till ak, the cost to compute that, let's say it's p1, and minimum cost to compute m of k plus 1 to j is basically p2. So the cost to compute this entire thing is p1 into p2, which is d of I minus 1 into dk into dj, because the last this entire thing is a matrix of dimension dk k cross j, and this entire thing is a matrix of dimension I minus 1 into k. So that's my total cost. And again, like you can see the tables here, so I'm not going to the details of the tables here. So you identify the order of solving the subproblems, and you again find your something called overlapping subproblems, and you simply can store these values, this values m and all, as a tabular memorization kind of thing, and you can just simply query. So you have something of called like a 2D array where you store uh, I and j are basically your row and columns of the 2D array, and you store the solutions and so on. So yeah, so I think that's kind of like I would just probably share this lecture note with you in the chat. I think due to shortage of time, I will probably go through the questions now. I think we are almost at the end now of. So basically, the matrix multiplication using this case is order of n cube, if you see with the kind of dynamic programming aspects and all. And in recent years, there is many sort of like proposals to reduce this time even more. So people have done order of n to 2.5 and so on also. So again, like this is not so important in the current course content. I think mostly it's about like how the questions should be now. So we'll discuss that, and probably we'll end with the recap of all the things that we have done today. So I think we are ending with week 8 now. So we have completed the week 8 topics, and I think for the other topics also we have also looked into. So we have looked at the different data structures, list and sorting and all those things, as well as with some aspects of the exception handling, input and file handling. And main problems on are the ones on dynamic programming and backtracking. So coming back to the questions now in the chat. So will there be questions like programming assignments? So okay, so the long programming assignments that you were seeing in the that you were given, those things won't be given in the actual exam because due to time limit constraints. They will be given numerical questions or simple programming questions like in the previous like where you was like some of the problems I had solved without even coding up the Python program. So those kind of problems you would see in your actual exam. So for example, you are given a Fibonacci series, and you are asked to say like what is the number at this position of the Fibonacci series, or you have dynamic programming wise Fibonacci series. You are asked to say what is the number stored at the table number position, this thing, and so on. So in this case, you don't need to solve any programming code any programming code or anything. You just have to analyze the program by through different ways of understanding how the program is structured and all. So many problems that I solved initially, if you remember in the initial few lectures, was that I didn't even solve the programming question. Like I didn't code out the programming question. So we used to solve it by just analyzing the code itself. So those kind of problems you would be expecting, and the bigger programming questions that you saw in your assignments, those won't be given in the actual exam because it's a time limited exam, and those programming questions would take a lot of time, so you won't be given those. So I would highly recommend you to practice already the short MCQ kind of questions that you have seen in your assignments and quizzes. as well as with some of the websites I have shared for Python quizzes. Like Geeks for Geeks is one of the more main popular examples. Then there is W3 Schools, and also I think HackerRank Python quiz is something that I mentioned. So those are kind of the things. So so I think that's the overall structure you can expect in the exam. The question patterns you can expect in the exam. So that's the kind of thing. So whatever you saw in the quizzes, those would be like similar to that question patterns. You would have same style of questions there, and the shorter problems in the assignment. So that means programming questions that were very of short length. You didn't have to write any programs, large programs and all. You can simply analyze the programs by looking at it. Those kind of problems you would be expected in the main exam. So that's the kind of thing. So there is another question, like any tips for final exam. So tip wise, I would say like I'll just request you to just go through the concepts once more, like revise through it. There are also like apart from the this lecture itself, obviously this is recorded. You'll see on YouTube all the lecture recordings. There is also professors, the actual professors course which is happening. You can also rewatch the videos and all. There is also different online resources if you need some help. As I mentioned, Geeks for Weeks is one of the most popular online resource for this. I would highly suggest to revise those topics. And I think that should be enough, I think, for this. And you should also side by side practice some quizzes. From Geeks for Geeks is one example of quiz. W3 Schools is one another example of quiz. Those are the things you have to you can do side by side. So don't think that would be kind of like a difficult thing. I mean, you can revise the topics once more and just do some short quizzes on the side. So that's the sort of advice or tips can say for the final exam. So another question from Sanjit. Last week 8 is very heavy. Can you please suggest me question pattern from this week? Okay, so dynamic programming, yeah, I would agree. It's kind of heavy, like it's a heavy topic, it's advanced topic in some sense. So for dynamic programming, whatever the problems that we discussed in terms of matrix multiplication, longest common subsequence, or Fibonacci, these are the popular three questions you can think of that you may get asked mostly in the question exam. So things like time complexity wise, you may get asked. So time complexity wise, like as I mentioned, like how you are reducing the time from data structure point perspective. For example, you stored it in a 2D array, the memorization table and all. You might get you might get a question in terms of, let's say, the pseudocode that I showed for, let's say, for longest common subsequence. You might have something like fill in the blanks in the pseudocode. Let's say the recursion problem Cij equal to the max of something like this. So you have some kind of fill in the blank, and in those cases you have to answer this kind of question. So that is one type of questions I can think of that you might get asked. The other is like some kind of like some short, simple Python dynamic programming, like Fibonacci sequence is a very easy dynamic programming thing. You might be asked to code on that. So that is one case. One example can be, I can give you an example. Say a special type of Fibonacci series can be like, so I mentioned Fibonacci is like f of n equal to f of n minus 1 plus f of n minus 2. So you can have something like f of n equal to f of n minus 1 plus f of n minus 3. Let's say instead of n minus 2, it's n minus 3. So in that setting, you might get asked question about the dynamic programming. Let's say the memorization list that you have. You might get asked a question. What is the value at, let's say, the fifth index of the list? Go in depth about the problems. We solve it by hand. So I think that would give you much topic. I think that's more or less the case. So So I will just type the quiz channels. One is Geeks for Geeks. So we'll end at 4 p.m. So just last 5 minutes we are. So one is Geeks for Geeks, one is W3 Schools, and one is Hacker Rank. So I'm just typing all this in the chat. So whatever time is remaining, you can make full use of this time till the exam with side by side going through the uh, division notes and all. So is the exam completely MCQ type or not? So yeah, I think it's not completely MCQ. There will be a mix of, as I mentioned, numerical kind of questions also and all. So it won't be multiple choice questions only. It would be like you have to type an answer, let's say. It won't be descriptive, but that's the kind of. So can you provide any references for dynamic programming? So again, like Geeks for Geeks is the main website for dynamic programming. So yeah, so Geeks for Geeks is something like the main sort of website you can look for any sort of. So yeah, I'm not exactly sure about the time and the total marks. I think you should reach out to the NPTEL coordinators beforehand. You can email them and sort of ask any doubts if you have. Okay, so any YouTube channel to refer to detailed explanation of assignment quiz. I'm not sure if there is any YouTube channel for that, but for dynamic programming and all, I would again suggest like there is this dynamic programming and the other thing was we were discussing about was on backtracking and all. Highly suggest like this YouTube channel called Abdul Bari, which is very helpful. I think I myself have also gone through that course during my time. So dynamic programming by Abdul Bari is on YouTube. You should go through this, like to get a more better understanding if you want, uh, because that's the sort of thing. Okay. So heaps also I would say like go through that same Abdul Bari YouTube videos. So I think for GATE and competitive exams, I think those are like they go into much more details. I think it's not needed for this course, but you can sort of go through that. So dynamic programming and feeds and all those with other structures, you can also refer to them. How many questions can you be asked? Can you please share the whole question over the question? Yeah, again, like I'm not exactly sure like how many questions are asked. There is a pattern followed every year. I would highly suggest you to reach out to the individual coordinators for this course. So you can email them directly for any questions like previous year question paper or not, so that they would give you some kind of idea about these things. I don't have those information right now, so that they would be the best person to reach out. So so there is another question. My assignment score does not cost 25 amount. So again, like reach out to PMRF, the NPTEL coordinator for this course. Any questions of any logistic questions you should ask them because they have the much more updated um, answers to it. Okay, so I think with that, I think probably we'll put an end to the lecture series. I hope you had a great time learning through this course, and I'm really fortunate to be sort of providing the lecture series in terms of helping you through the course also as a PMRF fellow. So again, for the question papers and all, please ask the integral coordinates directly for this course. Email them. There is an email provided with the integral website for this course, so that you should reach out to them for any questions in terms of exam logistics and all. So they are the ones who should reach out. So again, thank you once again for your time and through this entire lecture week had a, I guess we had a fruitful time learning through this entire thing. And best of luck to you all for the exam. Whatever time is left, I would highly advise you to go through, revisit the notes once more, and practice some problems through all the websites that I provided. And also, maybe if you haven't completely done the quizzes and all in the NPTEL thing. We should again practice it. So that's my advice and tips for the exam. Once again, best of luck to everyone for the exam, and thank you again for registering for this course and showing your enthusiasm throughout this entire lecture series. Thanks again. I think all the lecture videos are recorded and uploaded on YouTube. So if you have any questions or something, you can also post comments there, or maybe you can rewatch the videos there also for any sort of like reference. I mean, okay. I think with that, let's bid goodbye and well, best of luck to everyone who's writing the exam. Thanks. Yeah, bye.